Alright, I want to calculate the area between these two curves, y equals x plus 1 and x equals y squared minus 3. The x equals y squared minus 3 is a sideways parabola. I think of this, if you didn't have the minus 3, if it was just x equals y squared, that would be through the origin going sideways. But then the minus 3 shifts it 3 in the x direction here, down 3 in the x direction, so back over here. Anyway, if I look at my rectangles that I was using in the last video, there's not a consistent bottom function here. That over here, top is that sideways parabola, and the bottom starts off as a sideways parabola, but over here the bottom is this line. And so I'd have to break the integral up into a couple of pieces, and I think it's just easier in this case to think sideways. Okay? So what I want to do is I want to see where do these two things intersect, where are these points, and I'm going to set this up sideways in the sense that I'm going to do my rectangles now are going to be horizontal rectangles. So I'm going to figure out how long they are side to side and then give them a little bit of thickness in the up and down direction. Now that little bit of thickness is a dy. Right? So I'm going to have essentially a big X value minus a small x value. That would tell you how far across it is, and then times dy. So this integral is going to be dy, which means I want to know the y value, the lowest y value I'm interested in, and the highest y value I'm interested in. Lowest one, highest one. So I need to know where those two curves intersect. So I'm going to do a little bit of work here. Actually, I'm going to do the work over on the side here, so I'm going to slide sideways a little bit. Where do they intersect? Well, I'm interested in the y value, so what I'm going to do is I'm going to take this x and plug it in there. And I've got y equals y squared minus 3 plus 1. That is, the y squared minus 3 was that x, and then you got a plus 1. So this is actually quadratic in y. If I get everything over on one side, I've got 0 equals y squared minus y minus 2. And I think that factors y and y, 2 and 1. Let's put a minus on the 2 and a plus on the 1. Yeah, so y equals 2, or y equals negative 1. So this is negative 1 where it starts, and up here where it crosses is right there, positive 2. So I'm going to integrate from negative 1 to 2 of right minus left, big X minus small x. Well, the big X is the x value on this line. Well, x is given by the line here is x equals, I'm going to subtract the 1 over there, so y minus 1. So y minus 1 is the big X value, and then the little x value is on the parabola. Well, the parabola is, well, x equals y squared minus 3. Be careful with your parentheses, because you've got to be minus that whole thing. When you're looking for the distance between 2 points, if they're horizontal points, you just do the big X minus the small x. So right minus left. When we were doing vertical distances, we're measuring things this way, it was the big Y minus the small y, top minus bottom. So anyway, right minus left. And this should give us the area in between. Again, you can do this by hand if you want, or you can just type it into your calculator. Actually, before I type it into my calculator, one of the reasons that it's sometimes nice to do it like this, rather than doing it 2 separate integrals and then subtracting, is that you can combine some like terms before you try to do the integral. So in this case, I noticed that the minus 1 and the plus 3 will get together. So I've got a y minus y squared, and then a minus 1 and a plus 3 is a plus 2. So you can integrate this function instead of that one. It's just a little quicker to type in. Anyway, it's 4.5. If it's x is as functions of y rather than y is as function of x, then by all means set it up sideways. Distance across being big X minus small x times a little bit of thickness dy. Since it's a dy, that tells you that it's y values that you're looking for on your limits of integration. You're not saying, hey, x goes from here to there, so minus 3 to positive 1, because you're not talking about x's, you're talking about y's in this case. What's the lowest y? Negative 1. What's the highest y? Positive 2. Anyway, oh, I guess there's one last thing I want to say. I have seen some people on this problem do this. That they've got these equations, what I have, x equals y squared minus 3 and y equals x plus 1. They say, you know what, I don't want to do it sideways. I want to do this. I want to write this as y equals x squared minus 3, and this is going to be x equals y plus 1. So they just interchange the role of x and y, and then rewrite this one as y equals x minus 1, because that's what they're used to looking at. They're used to looking at y as functions of x. So they say, okay, I got my parabola that goes down, that's shifted down 3. And they've got y equals x minus 1, so intercept of minus 1, slope of 1. Right? And they say, oh, this is the region I'm looking for. And then they set it up in the normal way of top minus bottom for each spot, top minus bottom times the thickness. Well, the top is the line that's given by this, x minus 1, minus the bottom. Well, the bottom is now the quadratic, which is this one up here, x squared minus 3. And then the thickness that they're putting on each one of these, that little bit of thickness horizontal, is dx. And they're integrating it from some starting value to some ending value, and it turns out it's still minus 1 to 2. Notice that this is the same integral that we had before, it's just it got x's in it instead of y's in it. Well, it's still going to turn out to be 4.5. So this is an option. If you don't like doing things sideways, you can just interchange your role of x's and y's and do it vertically. Anyway, either way, there you go, calculating areas.